Welcome to the Explainer. Okay, so today we're diving into some really fascinating AI news. We're unpacking a rigorous, brand-new mechanistic study by Randir Kumar that investigates a massive mystery in AI memory architectures. If you've been following the latest in knowledge graph embeddings, you know that making models natively reason over multi-hop chains is basically the holy grail. Like deducing that if A is related to B and B to C, then A must be connected to C. Holographic memory has been pitched for a while as this elegant, perfectly mathematical solution to this exact problem. But as this new paper reveals, well, what works beautifully in theory sometimes hits a hard brick wall in practice.
So we're essentially looking at a detective story today. We're investigating exactly why the theoretically pristine math of holographic memory just seems to collapse in real-world scenarios. We already know that knowledge graph embedding models reliably predict single-hop links, but they traditionally lack any mechanism to process unseen relation chains. Enter holographic reduced representations. They compress, bind, and unbind symbols via a math operation called circular convolution. They're incredibly attractive because that binding is approximately invertible and associative. I mean, on paper, it absolutely should work. But the million-dollar question is, can it actually reason? Or is that capability just a mathematical illusion?
Right. To figure that out, we need to make sure we understand exactly what we're measuring. The core benchmark being tested here is zero-shot compositional reasoning. We're talking about multi-hop questions where the specific relation chains have literally never appeared during the model's training phase. The study evaluates this using the FB15K237 dataset, which is basically the gold standard testing ground for knowledge graphs. And it does so incredibly rigorously across 5 random seeds. This is the ultimate test of true generalization. You're asking the system to connect dots it has never explicitly seen connected before.
Let's take a look at the lineup of our 2 main suspects. The researchers evaluated 2 specific variants of holographic memory, and they paired each one with a modern hop field cleanup function. On one side, we have real-valued HRR, which uses continuous real numbers. On the other side, we've got phase-only Fourier HRR, or FHRR for short. Now, both of these variants make the exact same foundational promise. They can cleanly bind and unbind symbols. The goal of this study was super straightforward. Just measure whether this circular convolution algebra actually enables zero-shot composition, or if it just completely breaks down under the complex topology of a real-world graph.
Now, initially, the news is fantastic. The patient is completely healthy when it comes to basic tasks. Both variants prove to be highly competitive single-hop retrievers. The real-valued HRR achieves a filtered mean reciprocal rank, or MRR, of 0.358. which is a really solid, highly competitive score in this specific testing environment. FHRR is right behind it at 0.350. So for direct lookups, the holographic memory works exactly as intended. It retrieves individual facts reliably. Everything looks great.
But here is where the illusion completely shatters. When we move to zero-shot composition, both models just completely fail. The accuracy simply flatlines, degrading all the way down to random chance. And actually, scratch the idea that it might just be a hyperparameter tuning issue. It's not. The researchers ran exhaustive temperature sweeps across the cleanup functions, and the accuracy remained at chance across all cleanup temperatures. Neither variant can compose zero-shot. So you have to wonder, if the single hop works so well, why does chaining them together cause a total system failure?
To find out, the researchers went into full diagnostic mode. They localized the failure mechanistically by breaking down the 2-hop reasoning chain into 2 distinct probes. Step 1. They execute a hop1 query to see if the memory can find the intermediate entity. Step 2. They bind that intermediate entity to the next relation to try and retrieve the final answer. By isolating these steps, it's like a giant puzzle. They could pinpoint exactly which piece of the math was breaking down.
Let's look at the results of that first probe because it really builds our understanding here. Probe 1 shows that the first hop works beautifully. The memory recovers the correct intermediate entity with incredibly high fidelity, an MRR of nearly 0.9 for the HRR model. This is absolutely crucial because it tells us, definitively, that the fundamental bind-unbind algebra isn't broken. If the algebra was the issue, this very first step would fail. It doesn't. Yet even when this intermediate entity is verified to be 100% correct, the full 2-hop composition still fails.
So we move to the second probe, and this is what reveals the root cause of the whole mystery. The researchers pose the ground truth second hop fact as a standalone atomic query, completely bypassing the compositional chain. And the result? The memory only recovers it at 0.26 to 0.48 times its average atomic accuracy. Performance uniformly plummets. And this degradation happens regardless of relation fanout, meaning it fails whether the node has tons of connections or just a few.
The superposed memory just literally cannot effectively retrieve facts that belong to compositional chains, even when you ask about them individually. This exact drop-off points us to the major aha moment of the entire study. To quote the paper directly, the bottleneck is retrieval capacity under superposition, not bind-unbind algebra or cleanup mechanisms. The capacity and interference effect is actually present already at a single hop. It's simply that facts passing through compositional chains are intrinsically harder for the superposed memory to retrieve.
To really visualize what superposition interference actually means, think of it like stacking those old printed transparencies on an overhead projector. One transparency is totally clear, two might be readable, but as you stack more and more relations, which is exactly what happens in holographic superposition, the images just blend together into a muddy mess. The signal degrades structurally way faster than any cleanup function can ever recover it. The architecture simply lacks the capacity to maintain distinct entity representations when those relations are layered right on top of each other. And well, to make matters slightly worse, the researchers uncovered a secondary failure that compounds the whole issue, specifically for the Fourier HR variant. They proved mathematically in Lemma 4.1 that FHRR's softmax cleanup is not phase equivalent. What this means in plain English is that there's a serious architectural mismatch. During the normalization step, the cleanup function actually distorts the phase information, breaking the symmetry required for reliable unbinding. This amplifies retrieval errors massively whenever the initial hop is noisy. Ultimately, it makes the real-valued HRR the more stable baseline between the two, even though, as we saw, both ultimately fail at composition.
So if you are building knowledge graph systems today, what does this actually mean for your pipeline? Well, the actionable advice here is super clear. First, do not rely on HRR or FHRR with standard hop-filled cleanup for zero-shot multi-hop queries. You will absolutely hit a retrieval wall. Second, holographic memory cannot replace explicit multi-hop routing or differentiable reasoning layers that maintain distinct state channels for each hop. You need an architecture that explicitly separates retrieval from composition. And finally, hey, if you're already using holographic memory for direct single-hop lookups, keep using it. Its configuration remains completely viable and highly competitive for those tasks. Just don't ask it to chain unseen relations.
Which kind of leaves us looking toward the horizon, doesn't it? Redesigning cleanup functions or endlessly tweaking temperatures isn't going to fix this. The capacity limit is a structural bottleneck. Any viable fix in the future has to address how superposed vectors can store and retrieve overlapping relation chains without the signal just entirely collapsing. So the question I'll leave you with today is this: how will the field of AI architecture overcome this fundamental capacity limit of superposed vectors? It is a fascinating challenge, and honestly, solving it might just be the key to unlocking true native reasoning in neural memories. Thanks for joining me for this explainer.